Welcome to SERA Science, where the strangest mysteries of science are explained simply. What if time itself could slow down? Not in your imagination, not because your clock is broken, but because the universe actually allows different people to experience different amounts of time. Here's the strange part. You are already living in a universe where time does not pass at exactly the same rate for everyone. So why does time slow down? Let's find out. Imagine you have two identical clocks. You leave one clock on Earth and take the other into a spacecraft. Then you accelerate the spacecraft to an incredibly high speed. When you eventually return and place the two clocks side by side, something shocking happens. They don't show the same amount of time. One clock has experienced less time than the other. Nothing is wrong with either clock. Time itself has passed differently. This is called time dilation, one of the most mind-bending predictions of Einstein's theory of relativity. Experiments with extremely precise atomic clocks have confirmed that motion and gravity can change the rate at which clocks tick. But why? To understand it, you need to forget one thing you probably learned as a child. Time is not universal. For a long time, people imagined that one giant cosmic clock was ticking everywhere in the universe at exactly the same speed. 1 second for you should mean 1 second for everyone. Einstein discovered that nature doesn't work that way. The key is the speed of light. Light always travels at the same speed in empty space, regardless of how fast you are moving. And this creates a bizarre consequence. Imagine a simple clock made from a beam of light bouncing between two mirrors. Every time the light travels from one mirror to the other and back, the clock makes one tick. If the clock is sitting still, the light travels straight up and down. But now imagine you are watching that clock move incredibly fast across space. From your perspective, the light inside the moving clock doesn't travel straight up and down. It travels along a longer diagonal path. The light still has to move at the same universal speed. So if the distance it travels becomes longer, something has to change. The clock's ticks take longer. Time has slowed down. And this isn't just about clocks. If you were inside that spacecraft, you wouldn't feel your own time slowing down. Your heartbeat would feel normal. Your thoughts would feel normal. Your watch would tick normally. 1 second would still feel like 1 second to you. But compared with someone who stayed on Earth, you could experience less elapsed time. The faster you travel, the bigger the difference becomes. At the speeds of cars and airplanes, the effect is incredibly tiny. But as your spacecraft approaches the speed of light, the difference becomes enormous. Imagine traveling through space at 99.9% of the speed of light. You could experience a few years, while much more time passes for people who remain on Earth. You could return home expecting familiar faces, only to discover that decades have passed for everyone else. This is where time dilation becomes almost like real-life time travel. You aren't traveling into the past. Instead, you're traveling into the future faster than someone else. But speed isn't the only thing that changes time. Gravity does it too. According to Einstein's general relativity, stronger gravity means slower passage of time. Imagine two identical clocks. One is at the top of a mountain. The other is deep in a stronger gravitational field. The clock deeper in gravity ticks slightly slower. The difference is incredibly small on Earth, but it is measurable. And near an extremely massive object, the effect can become dramatic. This is why black holes are so fascinating. If you could somehow safely approach a black hole, time for you would pass differently compared with someone far away from it. From far away, your clock could appear to run extremely slowly as you approach the black hole's event horizon. Meanwhile, from your own perspective, your clock would still feel completely normal. That sounds impossible, but here's the most important idea. There is no single universal clock controlling the entire universe. Your experience of time depends on your motion and your location in gravity. And this isn't just some strange theory that only matters near black holes. It affects technology you use every day. Your phone's GPS depends on satellites carrying extremely precise atomic clocks. Those satellites move rapidly and experience a different gravitational environment from clocks on Earth's surface. Relativity causes their clocks to shift by measurable amounts, so engineers have to account for those effects. Without relativistic corrections, GPS positioning would quickly become inaccurate. So the next time you open a map and watch that blue move toward your destination, remember something strange. Einstein's flexible version of time is helping you find your way. Time isn't a river flowing identically everywhere. It's part of the fabric of spacetime. Move differently, and your path through spacetime changes. Enter stronger gravity, and your rate of time changes. And if you could travel close enough to the speed of light, you could experience a future that arrives much faster for everyone else than it does for you. So the next time you look at a clock, don't think of it as showing the time. Think of it as showing your time, because somewhere else in the universe, another clock could be ticking at a slightly different rate. And both clocks could be completely correct. That's the strange reality of time. If this changed the way you think about something as ordinary as a second, subscribe to SERA Science for more strange questions about the universe, physics, space, and the science hiding behind everyday life. And if you want more mind-bending science explained simply, like this video and comment, time is not universal. You might never look at a clock the same way again,